Welcome to the deep dive. Today, forget just crunching numbers. We're really digging into the ideas behind math, its structure, based on some really interesting work by Georg Pereskin and Maria Margotsch.
Yeah, they cover a lot of ground from, basic philosophy right up to things like a complete filling hypothesis and totally new takes on prime numbers.
Exactly. So our mission today is to pull out some, well, frankly, surprising insights about what mathematical objects are, the hunt for primes, and maybe some new ways to think about the whole number system. Let's jump in.
What really jumps out is the scale of these ideas. It's not just tinkering around the edges. These feel like potentially fundamental shifts.
Totally. And one of the first things I saw was this Parascan Jordan table. Now they're saying it's a revolutionary way to calculate powers of something called the Jordan matrix. For those of us maybe not deep in linear algebra, what's the big deal there?
Well, think of the Jordan matrix as a tool for complex systems, things that don't break down neatly. Normally, doing math with them, especially finding powers, is messy, lots of steps.
Yeah.
This Parascan Jordan table, it proposes a direct shortcut, no iterative multiplication, no complex diagonalization needed, just boom, the answer. And apparently it's been tested pretty rigorously.
Wow. Okay. So it's efficient and accurate. That sounds incredibly useful.
That's the claim. Tested on matrices up to 100 by 100, they say.
So the applications, I mean, you could be looking at analyzing stability in dynamic systems, right? Like in engineering or economics.
Definitely. Or maybe optimizing algorithms in AI, perhaps speeding up how machine learning models work.
And maybe even new types of cryptography, like hash functions.
That's another potential area, yes. And they even talk about extending it to radicals of these matrices, which might connect back to number theory and primes.
Which brings up a philosophical point, doesn't it? If this table is so efficient, does that suggest like an inherent order in math, a kind of mathematical realism?
That's the deeper question they seem to hint at. Does the elegance of the solution reflect something fundamental about mathematical reality itself, not just a clever human trick?
Interesting. Okay, let's pivot to primes then. Always a huge challenge, finding and verifying them. Pereskin and Margot's have ideas here too, like the formula Margot for primality. What's that about?
Right, finding primes efficiently is, well, it's a holy grail in number theory. This Margot formula uses logarithms and trig, which is different.
Different how?
Most primality tests involve lots of iteration looping calculations. This one's presented as more direct, and they claim it's accurate for absolutely enormous numbers, like up to 10 to the power of 30.
Whoa.
Plus, they mention using modular relations, basically remainder checks, to quickly rule out many composite numbers. It's about efficiency.
And I saw mentions of formulas for twin primes too. And this other one, the algebraic geometric formula, blending algebra and geometry for primes.
Yeah.
That sounds unusual.
It does. The idea is to combine insights from both fields. Algebra's power for manipulation, geometry's for structure. They suggest it scales well. Potentially usable even for numbers in the trillions, maybe manually or with computers.
And then there's a universal formula for groups of primes, like finding twins, triplets, all with one formula.
Yeah, apparently by just changing one parameter, it can identify these different consecutive prime groupings. If that holds up, it's quite something. A potential pattern generator.
Okay, moving into slightly more mind-bending territory. The complete filling hypothesis.
Yeah.
What exactly is that proposing?
This one's really out there, suggesting natural numbers aren't random, but form a kind of complete predictable structure.
A structure? How?
It involves different types of numbers, pure primes, resistant primes, composite primes, they call them all, fitting together perfectly. They even report finding a unified slope of 1.0 and 0 predictive error, implying the whole sequence is theoretically perfectly predictable.
Zero error, complete predictability. That sounds huge, especially for things like the Riemann hypothesis.
Potentially massive implications, yes. If primes aren't random but part of a deterministic pattern, well, that changes a lot in number theory.
So maybe the randomness we see is just our limited perspective.
Okay, and speaking of big perspectives, the Parascan and Margot's paradox on infinity, they're saying infinity isn't abstract.
Right, they're challenging that idea. They propose infinity isn't just a concept, but an endless ecosystem of actual measurable things.
Measurable infinity. How?
They introduce a constant k, which lets them relate infinite magnitudes, m, to finite measurable ones, m, so like m equals k times m. They even give a geometric picture. An infinite line is just the radius of an infinite circle.
Huh. So infinity has properties, like density.
Exactly. They suggest the density of an infinite universe could be constant and measurable. It's trying to make infinity less abstract, more physical in a way.
Wild. Okay, finally, bringing some threads together.
Right.
The Margot-Jordan table. What does this one do?
This seemed to combine their work on divisors, the Margot and Parascan table ideas, with the Jordan matrix framework we talked about earlier.
So merging number theory with matrix methods. Precisely. They suggest applications, again, in number theory, identifying primes, factorization, but also back in AI, maybe optimizing network weights or reducing data dimensions, and even cryptography for key generation or hashing.
And they talk about higher dimensions, up to 50D.
Yes, extending these table structures into many dimensions,
Sure.
which could be powerful for complex data analysis.
Okay, wow. So just to recap, we've got these novel methods for matrix calculations, new formulas aiming at primes, this unifying idea of complete filling for numbers, a whole new take on infinity, and this multi-dimensional table. It really feels like these ideas could ripple out, doesn't it?
Absolutely. Across math, computer science,
Yeah.
maybe even how we fundamentally think about reality and structure.
Which leaves us with a thought for you, the listener. If these perspectives hold up, could they change not just how we do math, but how we see the entire numerical universe? What other hidden orders, what patterns might just be waiting to be uncovered?